I want to try to convince you that the sum of squared total always has to be greater than or equal to the sum of squared within by definition. Now, I could prove it to you with math if I wanted, but I'm going to try to do it with a picture instead. So let's suppose we're comparing two groups, A and B. Here's some data points, and here's some data points. Here's the idea. I can calculate the sample mean in each of these groups, right? And see how far the points are from the mean in their own sample. Okay, and that would help me calculate SSW. Or I could calculate the overall mean, which is kind of somewhere in between. So I'll draw a line like this, or I could draw a dot in those lines, here and here, right? Okay, to calculate sum of squares total, I have to see how far each data point is from the overall mean. To calculate the sum of squares within, I have to see how far each data point is from the mean in its own group. Because each data point has more influence on the mean in its own group than the overall mean, because there are fewer data points in its own group than the overall data set, then on average, although not for every data point, the residual will be smaller for the separate means model than it is for the equal means model. In other words, on average, a data point is closer to the mean in its own group than the overall mean. It's not true for every data point, but it has to be true on average. And therefore, the sum of squares total, the total amount of variation in the data set, has to be at least as large as the variation, the sum of squares within each group. You can't have a bigger sum of squares within the groups than you do overall. So then that means that when we're trying to come up with a test statistic, remember that's what we're doing, we're trying to find a test statistic that will help us compare the means of multiple groups to each other. We can't just say, okay, which is bigger, SST or SSW? That's not going to work. The question can't be, is SST bigger than SSW? Because it always will be by definition. So by how much? By how much? If SST is way bigger than SSW, let me try to draw a picture like that, where SST is way bigger than SSW. If you haven't seen this kind of notation before, when you put two greater than signs, it means way bigger than. Here's a case where SST is way bigger than SSW. Here's the A group and here's the B group. Okay. There we go. In this case, SSW is going to be really small because within each group, the points are very close to the mean in that group. But SST is going to be really big, right? So here are the within group means to calculate the SSW residuals. But here is the overall mean for calculating the SST residuals. SST is going to be a really big quantity because each of these data points is very far from the overall mean, but each of these data points is very close to the mean in its own group. So this would be a case if SST is way bigger than SSW, it implies that the population means are probably different, right? I would believe that the population means are different from each other if I saw this picture, right? If I saw these data points. But what if SST was pretty close to SSW? Can I draw a picture like that? It always has to be, can't be smaller, but what if they were pretty close to each other? Well, that would look kind of like this, right? So here's the mean in each group, right? Maybe here's kind of the overall means, kind of in the same place, right? Well, if the sample means are very close to each other, then therefore the overall mean is about the same as each of those sample means. And so now the sum of squares within the sum of squares total are pretty much based on the same residual. They'll be very similar to each other. And so this is a case that suggests that the population means are not different from each other. Now, this is something you could have told me looking at the data alone. Clearly, the picture on the left has more evidence that the samples come from populations with different means than the right picture does. The right picture does not seem to imply that the samples come from populations with different means. But now we have an idea for how to actually quantify that idea, right? Quantify that discrepancy. If SST is way bigger than SSW, that implies that we think the population means might be different. If SST is not that much bigger than SSW, that suggests maybe the population means are not different after all. So our next idea is to calculate this discrepancy. This is going to be the discrepancy between SST, and SSW. Now, I'm going to calculate some differences and square them and add them up. I don't think you'll be shocked. In fact, let me start with that framework. Here we go. Here's my differences. I'm going to have 6 differences, 1 for each data point, and I'm going to square them and I'm going to add them. So that's nice and familiar. This is how we got to SST and SSW. For SST, I took each data point and I subtracted the overall mean. For SSW, I took each data point and subtracted the within group mean. Now, I'm going to take the within group mean for each data point and subtract the overall mean. I'm still going to do it once for each data point, but now I'm going to write down as the first number in each of these differences the mean within the group. So that was 4 for the values in group A, sorry, 12 for the values in group A and 4 for the values in group B. And from each of those, I'm going to subtract the overall mean, which was 8. Okay. And if I do this, the number I get happens to be 96. Okay. Just to make sure this is clear, this is the within group mean. This is the overall mean. Okay. Now, what do we notice about this quantity? Is there anything you notice? How does 96 relate to the values that you've seen previously today?